In this video, we have a lens combination. So they're labeled as lens number 1 and lens number 2. The first lens has a 20 centimeter focal length, and the lenses are 20 centimeters apart, which puts the second focus of the first lens sitting right on the second lens. The second lens has a focal length of 15 centimeters. This whole grid has been set up to scale, and every 2 spaces means 5 centimeters. In part A, we're asked to draw an accurate ray diagram for how the image is processed by both lenses, and we should be able to get reasonable estimates of the image distance relative to the second lens and the total magnification. So we begin by using the principal rays for the first lens. A ray coming in horizontally to that first lens is refracted through the focus. A ray coming in through the center of that first lens is unrefracted. And a ray coming from the direction of the near side focus from the head of that object is refracted parallel to the principal axis. Now on the right hand side, I see that we have 3 diverging rays, and we need to trace these back to a common origin. We see that all 3 rays have a common origin back here, and that's where we're going to see a virtual image of the head of the arrow form. And now that virtual image becomes the object for the second lens. So we start taking principal rays and processing them through the second lens now. So I have a ray coming in parallel to the principal axis. That's refracted through the focus on the opposite side of that second lens. I have a ray coming through the center of the second lens. That's unrefracted. And then a ray coming through the near side focus of the second lens. That's refracted parallel to the principal axis. And I see all 3 of these rays converging to a point on the opposite side of the second lens. So there's my final image. Now, a ray diagram isn't going to give you exactly the correct quantitative results, but it should allow you to estimate fairly accurately. So the image distance relative to the second lens, I can just count spaces on my grid and estimate that. And that's 7.5 spaces. Again, we're using a grid where every 2 spaces is 5 centimeters. In other words, every space is 2.5 centimeters. So I get an approximate image distance of 18.8 centimeters right of the second lens. And then my approximate magnification, as far as I can tell, it's really, really close to 1. So our original object was about 1.5 spaces high. Our final object is about 1.5 spaces high. It looks like it might be slightly less than that, but it's really hard to tell. So I'll say our magnification is about 1, maybe a little smaller. And just one final point on this slide, the magnification should come with a minus sign because I can see that my final image is inverted relative to the original object. Now we get quantitative. I want the image location relative to lens 2, and I want the total magnification. So really the best way to organize this is in terms of the processing of the image through the first lens, and then we'll do the processing through the second lens. So I write down what I know with that first lens, and I was told that my original object distance, so I'll call that DO1, was 15 centimeters from a lens with a focal length of 20 centimeters. So I used the thin lens equation, and I solved for 1 over the image distance for that first lens. That's going to be 1 over the focal length for that lens minus 1 over the object distance. And you can do this all at once in a calculator. You do 1 over 20 minus 1 over 15, and then take 1 over that answer. And when I run the numbers, I get an image distance of negative 60 centimeters. In other words, it's a virtual image on the left side of that first lens, just like we saw in the ray diagram. My magnification at that step is going to be negative DI1 over DO1. And when I plug in the negative 60, I end up with a positive result, and that's 60 over 15, so it's a magnification of plus 4. So the first image is 4 times taller than the original object, which also agrees qualitatively with what we saw in the ray diagram. Then I look at the processing through the second lens. And my object distance, well, I'm using my first image as the object for the second lens, and my first image was 60 centimeters to the left of the first lens. In addition, the lenses are 20 centimeters apart, and this means my object distance is 80 centimeters. My focal length for the second lens was 15 centimeters. I plug into the thin lens equation, solving for 1 over DI2. That's 1 over the focal length, which was 15, minus 1 over the object distance, which was 80. I smash those numbers in my calculator and take 1 over the answer, and I get DI2 is 18.5 centimeters. So that's the answer to part B. And it's pretty close to the 18.8 centimeters that we predicted from our ray diagram, so that's good. Then I go on to get my magnification at the second step. Again, negative image distance over object distance. So my image distance was positive 18.5, object distance positive 80, so I get a negative magnification, which is good because this is where we saw the image get inverted. And I get a magnification of negative 0.23 at this step. The only thing left to do is part C, the total magnification. And magnifications are just a scale factor telling you how much bigger or smaller the image got at each step. And if you just multiply those as you go through a series of lenses, you get the total magnification. So our total magnification is negative, which is good. We saw a final image that was inverted. And I kept some extra digits in my calculator, so I get negative 0.925. From our ray diagram, we knew that the magnification was going to be very close to -1 and probably a little smaller, so that looks great. If you find the physics content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce over 100 new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.